Hi, my name is Daraja Brown, and this is my charged tapes lab. So the purpose of this lab is to explore electric force interactions between charged objects, in this case, clear tape, to determine the amount of excess charge of the tape and to create a program modeling this interaction. The models used were 2 pieces of standard Scotch tape, and then a computational model was made with Python to calculate the charge of the tape. Some principles used were Newton's second law or static equilibrium, in this case saying that the net force of an object is equivalent to the change in momentum over the change in time. Since there's no change in momentum, however, the sum of all external forces is equivalent to 0. And then the force of gravity here is equal to negative mass times gravity in the y direction, and the electric force is the electric charge times the electric field. And then the electric field formula is shown here, which is 1 over 4 pi epsilon naught times the charge squared over the distance between the two objects squared. So here's a brief overview of the results we'll see in a little bit. Tape B was the floating tape, and it had a length of 0.2 meters, and the mass was 2 times 10 to the negative 4th kilograms. And then the tapes were repelled at a distance of 0.035 meters. And then we will come back to this table at the bottom later, but basically you can see that the experiment and computational model had the same results. So the system for the experiment was tape B, and the surroundings included the Earth, tape A, and then the air, whose effect was ignored as air resistance. And the initial condition was that tape B was rested flat and did not float yet due to the lack of a charged object nearby. So key assumptions needed for this experiment are that we're going to ignore air resistance, we'll treat the tape like a point charge, and we assume that each tape has the same amount of evenly distributed charge throughout it. So the process was that 2 pieces of tape were charged by laying them on a third piece and removing them quickly. Then tape B was attached to 2 blocks and suspended horizontally as shown in the picture. Then tape A was brought towards tape B from below, and the distance between the tapes was measured when tape B began to float. The rest of the process was that the length of tape B was multiplied to find the mass, and then the force of gravity and the electric force were calculated using the formula shown before, as well as the charge of the tape. Then the number of electrons was calculated using that 1 electron is equivalent to 1.6 times 10 to the negative 19th coulombs, and the ratio of deficient electrons compared to the total number of atoms was discerned. Here's the code for the computational model. As you can see, it represents everything shown in the formulas that were done in the hand calculations. So we have some of our constant values. We created objects for tape A, tape B, and then the arrow is the electric force between the two. And then this is what that looks like. So we have tape B. This is the electrostatic force from tape A onto tape B. Here's tape A. And we can see that the charge on the tape and the force of electrostatic force is shown here. So coming back to the results like before, we found that the force of gravity is equivalent to the force of the electrostatic interaction, and that's 2.03 times 10 to the negative 3rd newtons. The Q charge was 1.66 times 10 to the negative 8 coulombs. We found that 1.04 times 10 to the 11th electrons were missing from the tape, and there were a total of 6 times 10 to the 17th atoms in tape B. And overall, that comes out to a ratio of for every 5.78 times 10 to the 6th atoms, there was 1 electron deficient. Some similarities and differences. The results were the same because that computational model was based on the observed values, but some possible sources of error were that we didn't account for air resistance, the distance between tapes was slightly estimated, and the ruler only measures to millimeters, which can cause large differences when we're dealing with atoms and electric charges. But what if the electrons had a positive charge and protons had a negative charge? Well, that would mean that the electric fields would change direction, but everything else would be the same. The tapes would still both be negative and repel each other because they're like charges. And same thing with everything else that they currently attract, like my hand, cell phone, pen, water bottle, etc. Now, why is it important to handle the charged tapes as little as possible? That's because as a negatively charged object comes into contact with positively charged tape, the electrons would transfer into the tape, and that would decrease the positive charge, therefore interfering with our experiment. So in conclusion, the Scotch tape was positively charged, and overall this shows how household objects, some knowledge, and a little bit of creativity can be leveraged to explore the principles of science and understand the universe around us. Thank you.